Oh, why, hello there. I didn't notice you. Oh, you just happened to catch me in the middle of a wonderful game called Railway Empires. What does this have to do with engineering content, you may ask? I'm so glad you inquired. You'll notice some fundamental equations back here on the whiteboard that appear to be mostly unrelated. Okay, let me drop the sort of weird, soft professors baiting content voice, but um, today's going to be kind of fun. It's a little bit different. Um, we're taking a slight detour from the fundamental engineering content that we will get back to, especially as we step up to 2 content releases a week, to do an excursion that I've been thinking about for a while that might be kind of fun. Um, let's start back here. And we'll call this, actually, I should probably change this title here. Fundamentals of Continuum Mechanics. Engineering. Sure. Why not? Okay. Fundamentals of Continuum Engineering, or Continuum Mechanics, if you will. Uh, this is a really interesting topic within the field of engineering. For many reasons, fluids in particular is near and dear to my heart. I did a decent amount of sort of fluids propulsion and compressible fluids for studying propulsion systems in undergrad, as well as CFD and even a little bit of MHD, but not authoritatively. Just was not a physics PhD, just enough to treat the topic with respect, shall we say. But one of the reasons that continuum mechanics is so interesting is that it's applicable. It's a nice generalized form that's applicable to almost like an engineer's stat mech or statistical mechanics. It's applicable to so many different ways where you can take very powerful concepts and apply them across compressible fluids, incompressible fluids, and statics and stresses and dynamics and all, or very like finite element analysis. And it's really, really cool. So we're going to break this down again. So we're targeting sort of like a second or third semester undergrad engineering student level here. We're going to look at some interesting ideas. We're going to find some fun ways to explain them and think about them. And we'll start back here. I have a sketch thing on my tablet wall, so I use, but we're going to focus on this equation in particular. So this is Reynolds transport theorem, RTT. And if the calculus is too much, let me break this into a couple of pieces. Basically, the change over time for a volume itself of a particular vector field can be expressed as the sum of the integral of the derivative of that field with respect to time plus over the differential of that field, the integral of the dot product of velocity of the vector field, the normal of its change, and against the vector field itself, integrate over the area, right? So that's the unit area that's changing. So you have basically 3 pieces here, and if you think about it, this is just sort of like a complex expression of the product rule in calculus, right? Um, differenticities plus times that plus the difference of this piece times that, right? So it's not particularly crazy. Where it gets really interesting is the fact that this is really like this F, right? This is just some sort of spatial representation of a volume, typically. But this F can be anything. And in particular, when you start breaking down like the tensor representation that lets you characterize this product, if I remember correctly, you can start drawing some very interesting applications to a lot of different fields. So basically, we call it the transport theorem because something is being transported across a boundary, and that boundary may actually be changing over time. So to just give you a sneak peek of how useful this characterization is, here's 2 other equations. This is the Cauchy, what's it, a momentum equation, I think? The conservative form of Cauchy momentum equation, and you can see, so here's the tensor field popping out, for example, right? Here's your vector field. In this case, we also have a gradient of momentum because the fluid itself is in motion. But by and large, right, so these terms are somewhat unique. But by and large, you can see a lot of the same characteristics coming through here. In fact, this may actually be like a breakout of this product minus that, right? If that's moved over to the right-hand side. And then the really fun part down here is this is like the fundamental equation of hydraulics. This is incompressible conservative form of Navier-Stokes. So in this case, you have the gradient of entropy. Here's the double dot product with respect to the field, momentum changing over time for that vector field. It's all here, right? All of these things can be derived with the right, basically with the right choice of the F, right? And the right handling of that F with respect to this product. So very cool stuff, but this is all just symbols, right? This is kind of overwhelming, and it doesn't really tell you much about how this can be used. So let's take a very simple case here and go back to our screen here. So this is Railway Empire. It's sort of like a railway tycoon successor, in which there's, in this case, this is a Germany map. You have different cities. You connect those cities with rails. Those cities consume different goods that you can connect from the countryside. For example, there's a cloth station here that's bringing in goods to be manufactured into clothing here at this station, as well as hops to make beer, wheat to make bread, etc. So if you look at the details of a particular city, what you will see here is a couple of interesting values. This is how much of that resource is in stock. This is how much is being generated, like what the differential is, how much is being manufactured, etc. So let's consider, for example, let's say, and as different satisfaction of those requirements for different goods are met or not met over time, the city will grow or contract. So I think it's 60% is the magic number. If 60% of the demands for that given city are met at any given point in time, then the city will grow. So this is a particularly difficult scenario for Germany, where you have to get 10 cities to 120,000 people, which is like getting one city takes some deliberate effort. Getting 10 is actually very difficult. So there's a lot of emphasis in this game placed on managing the flow of goods into and out from a city to make sure that demands are satisfied and the city can grow. There's a lot more that goes into it, but that's sort of the fundamental mechanic of the game. So you have to understand the flow of goods. And there are many different goods, almost like a vector space of goods that must be satisfied for that city. Let's simplify this for one moment, though, and take one particular good. Cloth is a good example here. So we have between 4.9 and 5.20 units of cloth. I think that's per week. I disabled the tooltips. Let me see if I can. Usually they just get in the way. Tooltips. This will help us explain some of the details. Here we go. All right, so this is how much is in the city. This is the demand. This is how much is being manufactured. Here's demand for all cities, all businesses. So in the case of cloth, the tailor is making clothes that are also in demand by other cities. So let's draw a line around the boundary of this city, right? And let's use a darker color to do that. I have a 4-track station here. This is Frankfurt. Let's establish a boundary, right? So this is the omega, right? The surface or the volume. We'll assume it's constant for now. And let's consider see, vector not set. So this is should we do cloth or let's do cloth. Okay, so when you consider sort of the integral about the boundary of the flux of that cloth going through, how do you characterize the change over time of cloth within that volume, right? So there is, of course, some constant amount of cloth there at the beginning of any point in time. And then we need to consider, let's see, actually, let's do clothing because that will be more interesting. There's more variables. So there is some quantity of, or rate, right? Because we're thinking about this as a step in time, and then the time steps can become infinitely small, so we can integrate infinitely many of them. The power of calculus. Let's just call this C. So there is some rate at which clothing is coming through this boundary, so integrating cross flux, right? So C dot in. There is some rate at which clothing is leaving the boundary, C dot out. Let's assume those are all positive values, and we'll use negative values to indicate the departure, although mathematically that would be reflected, that would be captured by the dot product of the flux through the boundary, so we wouldn't necessarily need to have signs. There will be some degree of cloth produced within the city, and there will be some amount of cloth consumed. Again, we'll use the negative to indicate that. Right. So this is an expression for the rate at which this resource changes within this boundary, given flux into and out of that boundary. So let's just call that C dot. And now we can start assigning values. We said clothing, right? So this is stock in city. Demand, basically that's consumption, right? So we know how much is being consumed. We can look at the factory to determine how much is being produced. It's 1.2 at the tailors. There's probably, it's 1.5 now. Already we can tell more is being consumed than produced, right? Some of this would be shipped to other cities, and then other cities might bring some in. So the fundamental mechanic of the game is to determine how much resource must be provided into the city, and basically negotiate that as a function of your transportation network. So let's, given that, try and optimize that relationship. So we need, let's look at wool, for example, as sort of the ingredient that goes into that. We have some characterization of cloth. Let's consider, let's add another component to our equation. So now we actually have a vector. Okay. So there is a certain amount of wool required for basically consumed. One is consumed. I can't remember if that includes the factory use capacity. Let's assume it doesn't. So this is how much must be provided, right, as a rate. What we see is, let's go to the station here. Frankfurt. There's 8 units per car. And we know the city requires, through this boundary, 3.3 units per week. So the question becomes effectively one of velocity, that is, how long does it take each train to get there, and how many trains are there, right, to perform one cycle. So in this case we have 4, and it will tell us what the round trip duration, 116 days. That's 16.5 weeks for that one. 96 days. I feel a spreadsheet coming on. That wheel got stuck, didn't it? Ooh, that's going to make me nauseous. Okay, let's assume that averages out to 100. So 14 weeks per trip. Or line. And we have 1, 2, 3, 4 lines. Let's see, units per line or train. And of course we have 4 trains. So now here's some dimensional analysis, sneak peek for next units course or units segment in the course, right? So how much is coming into this boundary? We have a certain number of trains. So this is as a function of time. So what is the rate per week in this case? Certain number of cars per train or units, etc. So if we have 4 trains, each of which is carrying 8 units, and they're repeating their run every 14 weeks. Am I doing this correctly? I might not be doing this correctly. Let's sure. This is about 2.3. And now let's make sure the units work out. So 4 trains. Always start with your scalar units. You can convert the rest. 8 units per train. 14 weeks per train. Although that's arbitrary, right? That's just 14 weeks. So in this case, this comes out to 2.3. What? Trains cancels out, units per week. Voila, look at that. Of course, one of these numbers is less than the other. But now you can back out, right, in this case. Let's say that's n. You can back out the number of cars that are required, or number of trains that are required. And that will give you the right flux that you need across this boundary to ensure that this value is greater than or equal to 0. So there's something we haven't talked about here, which is, I'm trying to think of the appropriate fluids analogy. There's only so much volume of traffic on the channels or the tracks that are provided. So at some point you exceed the saturation volume of that city in this case has capacity for, in which case you have to start expanding basically the number of tracks, which doesn't go above 4. So in that case, you start adding warehouses to the city. So that's another, and then there's now another constraint is time at junction. So if you have too many trains, one of the ways you see that failure mode occur is that the trains will back up into junctions, which will back up and back up and back up, and eventually you'll have recursively cycles of stuck traffic. So as you expand to warehouses, you use dedicated lines to attach to either stations or other warehouses at other volumes. So you actually, that problem actually becomes a little bit simpler because you have specific dedicated connections to and fro with dual tracking. And that would, so basically you're eliminating the need for junctions. You're for each warehouse there's 4 dedicated at least resources, and then you can duplicate resources based off of the coverage. Basically this is where I'm really getting at, for the given station as well as the city. This volume expands, and as a result your capacitance for flux across that boundary increases. as well as at the individual station. Your capacitance for egress from that volume increases as well. So I didn't want to make this a whole tour. I was thinking of doing like a dedicated weekend gaming episode where we go through this scenario and guide it. But I also wanted to talk more about the transport theorem and the kind of fun way that this captures it. So let's go back and review for a moment. We have a couple of key ideas here behind the transport theorem. The first is that there is some vector field that is changing within a volume that itself may be changing. And to calculate or characterize that quantity, you need to be able to integrate it across the change in the field. So remember that separates into two terms. So you integrate the change itself and you integrate, what's it be done, N dA across the change in the boundary, right? So this is dt, f dt. Let's say 3 ideas. So the next is, basically this is a conservation law, and that's all the transport theorem is at the end of the day, right? It's a conservation law expressed as a vector field using Gauss's theorem for integrals. So we have some vector of resources, right? And the change over time was the change of that field. So we actually didn't walk all the way through this. I can do that now. We said what? In minus out, and then produced minus consumed. And these are rates, of course. But this is just the integral of the flux, right? Because we don't need the sign. This is basically saying it goes in one way and out another way, and we can dot that against the volume. So this is the flux across the boundary. And this is the internal generation versus consumption. This is particularly relevant for, you could probably imagine, like thermal reactions, right? Thermal energy is being produced and consumed. So this is a difference between those is over time as opposed to space. So this is basically this for a fixed volume. And then the third interesting lesson was the units conversion, right? And again, we'll go into this in more detail. Given some scalar unit, you can convert from, let's say, to a desired unit from some initial unit by conversion factors expressed as fractions, and then those units will cancel out until you get the desired unit. There's probably more I could say on this. Let's see. No, without going into the details of like the train routing and things. So that's probably enough for now. I would love to find more ways to, especially for like resource management, etc. You can tell this game can get a very like Factorio feel, especially as you cascade or escalate different tiers of manufacturing resources. that consume and aggregate resources across cities. But that's probably enough to sort of give you the high level picture of the details. We will have a specific unit later on that goes into more specifics about fluids in particular, as well as sort of, we'll do a stress strain as well, but it won't be as continuum oriented. May do some basic logistics handling, but you can imagine this is just as applicable like operations research and logistics and synchronization. Yeah, I hope you're excited. I'm excited, but this is kind of a fun detour. Take care.